Today we're going to be covering Module 18, which is Vision and the Perceptual Organization and Interpretation. This is a really cool chapter, as you'll see some of these visual illusions that we've often seen, and I'll give you some explanation for that. So maybe those of you who've taken physics before in high school will remember this, but vision is really part of kind of energy, sensation, and perception. So we encounter waves of electromagnetic radiation, which is the spectrum. You've probably done those experiments with the prism, and you can bend light and it comes out in a rainbow. So those are the visible parts of the spectrum, and that's what we can see. But it's not really this light that we're seeing. We're seeing really this electromagnetic radiation, and then our eyes are responding to some of these waves that we are able to see. And you can see that they're gamma rays, X-rays, ultraviolet, infrared, and all that stuff that we cannot see, but we have that small little bit of the rainbow there. And then our brain turns these waves, energy waves into sensations. Energy wave sensations into colors. And so based on the waves that are hitting our neurons, then it's turned into colors. So in order to view color and hue and brightness, we perceive the wavelength and frequency of the electromagnetic waves as color or hue. So short waves, which are high frequency ones, end up being bluish, and then long waves are low frequency ones, and they end up being reddish. That's how our brain translates them. And then we perceive the height and amplitude of these waves as intensity or brightness. So those with high amplitude, so they're big waves going up and down, are bright colors, and then those with a small amplitude, which are kind of more low little waves, those are dull colors. So this is kind of the anatomy of the eye. You can see that the front is the lens, the pupil, the iris, and the cornea. And then the back of the eye has the retina, the fovea, the optic nerve, and the blind spot. And so you'll see that the image that's perceived by the eye is actually inverted within the eye itself. And then when it goes through the brain, it's then reverted back so that we see it in the proper direction. So light from the candle passes through the cornea and the pupil, gets focused and inverted by the lens, and then the light then lands on the retina, where it begins the process of transduction into neural impulses to be sent through the optic nerve to the visual cortex, where it's interpreted by the brain. The lens is not rigid. It can perform accommodation by changing shape to focus on near and far objects, and that's why you can actually touch your eye, and it's somewhat malleable, and your contact lenses, for those of you who wear them, are malleable. So here is kind of a more in-depth view of the retina. So light entering the eye triggers photochemical reaction in the rods and cones at the back of the retina. The chemical reaction in turn activates bipolar cells. It's different than obviously bipolar disorder, but these are bipolar cells. And these bipolar cells then activate the ganglion cells, the axons of which converge to form the optic nerve. This nerve then transmits information to the visual cortex via the thalamus in the brain. And so this is, remember how we talked about how nerve impulses are transduced, and then we have to have the action potential. So that's all of what's going on when we see these images. And so there's a lot going on inside our body that we're not aware of at all times. So we also have a blind spot. So there's an area of missing information in our field of vision known as the blind spot. This occurs because the eye has no receptor cells at the place where the optic nerve leaves the eye. To test this blind spot, walk slowly up to a screen with one eye closed and the other eye fixed on a dot, and one of the phones will disappear. So if you look this, so as you have this in front of you, cover one eye and then walk towards this looking at the dot, and eventually as you get to a certain point, some of the phones will disappear, and that is your blind spot. So photoreceptors are the rods and cones, and they're on the right, bottom right is a kind of a magnified image of what rods and cones look like. So when light reaches the back of the retina, it triggers a chemical change in the receptor cells called rods and cones. These rods and cones in turn send messages to the ganglion and bipolar cells on the optic nerve. Rods help us see black and white actions in our peripheral view and in the dark, and rods are up to 20 times more common than cones, which help us see sharp colors in bright light. So when we have a accommodation, that's kind of our rods. For example, when you turn out the lights, initially you can't see it all, but then the rods can kind of come into play. So you can see that there are a lot more rods than cones. The cones are in the center of our retina, where the rods are in the periphery. The cones have very low sensitivity in dim light, whereas rods have high sensitivity But cones, on the other hand, have high sensitivity to detail and color, whereas rods have very low. The rods are the more crude kind of, if you think about when you look and seeing things in the dark, you don't see a lot of detail, but rather kind of shadows and outlines. So the images that we see are not made of light, they're made of neural signals which can be produced even by pressure on the eyeball. So once the neural signal enters the optic nerve, they're sent through the thalamus to the visual cortex. And if you remember from our previous lecture, that's kind of located at the back of the head. So you can see on the right, those are our eyes. The retina goes through the optic nerve, through the thalamus, and then the thalamus goes back to the visual cortex, and then it repeats that. So how do we turn neural signals into images? So some ganglion cells in the eye send signals directly to the visual cortex in response to certain features such as visual patterns, certain edges, lines, or movements. In and around the visual cortex of the occipital lobe, the supercells integrate these feature signals to recognize more complex forms such as faces. And so you can see the different areas of the brain which, look at faces, houses, and chairs. These are our supercells. And we know this because of studies such as fMRI and things like that, where certain areas of the brain are lit up in response to different stimuli. So parallel processing is turning light into the mental act of seeing. So we see light waves, they form chemical reactions which then send neural impulses. We then perceive different features with the supercells, and then we perceive objects. And one more step is called parallel processing, which refers to the building of perceptions out of sensory details processed in different areas of the brain. For example, when we see a bird, a robin, for example, we'll see the different colors, the red stomach, the black of the head, and the yellow of the beak. We'll see the movement, we'll see the outline of the form, and we'll see the depth perception. And then our brain puts those together and it tells us that this is a bird. So it's kind of a circular process. So, we have the scene at the bottom, the retinal processing, where the rods and cones go to the bipolar cells and the ganglion cells. Then they form the neural impulse, which then has feature detection. The brain's detection cells respond to specific features like the edges, lines, and angles. Then we have parallel processing, where a brain cell teams together to get the information about color, movement, form, and depth. And then that's when our brain kind of recognizes, we have recognition. And so it interprets all these different sensory inputs and tells us that based on what we know, that red, orange, and black stripes that moves fast and has that shape, that is a tiger. So when we think about perceiving color, there's the Young-Helmholtz trichromatic theory, or the three-color theory. According to this theory, there are three types of color receptor cones: red, green, and blue. And all these colors we perceive are created by light waves stimulating combinations of these cones. So we're mixing together the different cones to get these different colors. So when somebody is colorblind, they are missing red or green cones, and they have trouble differentiating red from green, and thus have trouble reading numbers on the right. So if you have color blindness, you won't be able to see the numbers on the right hand side. So if I can see correctly, on the top it's 45, and it looks like on the bottom it's 74. Opponent process theory refers to the neural processes of perceiving white as the opposite of perceiving black, just like yellow versus blue and red versus green are opponent processes. So keep staring at the dot at the center of this image. So you're focused on the dot. Okay, keep looking at the dot. And now can you see the lines that are there? It's pretty cool, right? So we have perceptual processes for enabling us to organize perceived colors and lines into objects. We can group incomplete parts into gestalt wholes. And so if we see figures standing out against a background, we can still, perceive the background because our brain fills in the spots. So we can perceive from form, motion, and depth. And it keeps the sense of shape and color constancy despite changing visual information. And so we use our experiences with this visual stimuli to guide our visual interpretation. So the roles of perception. So look at the image on the right. Our senses take in the blue information on the right. However, our perceptual processes turn this into a white paper with blue circle dots with a cube floating in front. A white paper with blue circle holes through which you can see a cube, and a cube sticking out to the top left or bottom right. So you can see, depending on how you view it, that our mind can fill in the blanks. So The blue dots with angle lines inside. In most visual scenes, we pick out objects and figures standing out against a background. Some art muddles this ability by giving us two equal choices about what is the figure and what is the ground. So, for example, when you see this, do you see a goblet or do you see two faces? So you can kind of look at the white or you can look at the blue, and you can kind of go and change that. And is this a stepping man? Is this somebody walking? Or these two arrows? So by looking at the front or the back, you can see, like, just by focusing on the white things, it's the arrows. The black is a man walking. So Gestalt refers to meaningful pattern configuration or forming a whole that is more than the sum of its parts. So there are three ways we process visual information as wholes. There are proximity, continuity, and closure. So proximity, continuity, closure. So one cool thing is called the visual cliff, which is our test of our depth perception. And we developed depth perception around the time that we start to crawl. So they did experiments with babies. And so, you know, a little kid wouldn't understand that he could potentially fall at the end of this mat. However, this little baby knows that he's not going to go any further, even though his mom is calling him, because there's the potential that he may fall, although he cannot because it's a glass table, but he doesn't quite realize that. So even newborn animals fear the perceived cliff. So we perceive depth based on 2D images using binocular methods. So binocular means using both eyes to form cues, and they exist because humans have two eyes in the front of our heads, hopefully, and this gives us retinal disparity. So people who only have one eye often don't have depth perception. The two eyes have slightly different views, and the more different the views are, the closer the object must be. So an extreme example, your nose is so close that each eye sees the complete opposite half of the view of it. So if you try to look at your nose, each eye sees the complete opposite view. So how do we perceive depth from a 2D image? By using monocular or using one eye cues. So one of those is interposition. So when one object appears to block the view of another, we assume that the blocking object is in a position between our eyes and the blocked object. So therefore, we perceive, you know, in the top right-hand drawing that there's a man, you know, behind some trees, even though they just actually take it out and we can see the horse. We don't think that it's just parts of a horse. And in the bottom, you see the Christmas trees, and even though we can't see some of the trees from behind, we can imagine that they are whole trees. We also look at relative size, so we intuitively know to interpret familiar objects as further away when they appear smaller. So if you look at the greenhouse picture on the right, we would think that the flowers in the back are further away than the flowers up front because they're closer. And then the little cartoon says, I have no depth perception. Is there a cop standing on the corner, or do you have a tiny person in your hair? Monocular clues also have linear perspective and interposition. So the flowers in the distance seem further away because the rows converge. Our brain reads this as a sign of distance. So we also, here's another example using linear perspective. So these two lines meet the retina as being the same size. However, our perception of distance affects our perception of length. So even though these two lines are the same length, the way that they're kind of focused in the drawing, we think that the one further away from us is actually longer, when in fact, if you kind of take your fingers and look, they are the same length. See? We also look at relative height cues, so we tend to perceive higher part of a scene as further away. So this scene can look like layers of a building with the highest part of the picture as the sky. Or if we flip the image, then the black part can seem like the night sky because it's now the highest part of the picture. So shading helps our perception of depth. Does the middle circle bulge out or curve inward? How about now? So that was just shading. So light and shadow create depth and cues. So this is the craters of the moon, and we can see by the way that light is bouncing off of them that we can perceive depth inside the craters. So motion is also a monocular clue. So when we're moving, we can tell which objects are further away because it takes longer to pass them. So if you're ever going in a train, if you fix on a point, those images that are things that are further away would zip by at a slower distance than those that are closer. So a picture of the moon on a sign would zip behind us, but the actual moon is too far to pass us. So we perceive motion in many ways, objects moving toward us. So we perceive this motion by watching the changing apparent size of the objects moving to one side. We perceive relative motion, although we often judge huge objects inaccurately. And why do we do that? So objects traveling a more complex path, such as an arc, in the air coming towards us, like baseball players or dogs, can run right to where a ball is going to land by keeping the ball in a constant apparent position in the sky. So, oftentimes it's hard to tell exactly where it's going to land, but if we keep it kind of in a constant position, we can judge where it will be. So our ability to see objects as appearing the same even under different lighting conditions at different distances and angles is called perceptual constancy. And it's a top-down process. So we often perceive color and brightness as being constant, even though it may vary depending on the lighting, as well as shape and size, even though those things may vary as well. So here's an example of color constancy. The ability to see a consistent color in changing illumination helps us see three sides as all being yellow because our brain compensates for shading. So we can see this image, even though the one on the right is almost black, we still view this all as the same color, even though it doesn't look the same because we know that it's different shades. So we interpret three same color blue dots with shades that are not adjusted for shading as there being three different colors. So brightness constancy. On this screen, squares A and B are exactly the same shade of gray, which is hard to believe. We can see this when we connect them. So why does B look so much lighter than A? And that's because it's being surrounded by different colors, which impact the way that we view them. We also have shape constancy. So shape constancy refers to the ability to perceive objects as having a constant shape despite receiving different sensory images. This helps us see the door as a rectangle as it opens, even though it's no longer a rectangle, because we know that doors don't necessarily change in shape as we open them. But you can see in the drawing, once we take away the visual cues, that these are really actually very different shapes. And then the moon illusion. The moon appears larger on the horizon than overhead. So why do we perceive the moon as a different size depending on its location? So one possible theory is that our ancestors assumed that overhead objects were closer than objects on the horizon. The moon, like one of these monsters, seems larger because we see it as further away. This is kind of an interesting visual a perceptual playing with our mind. So we have the ability to use distance-related context cues to help us see objects at the same size even if the image on the retina becomes smaller. So these two women are the same size, but there's this very special room that's created which can really morph the way that we perceive them. So this is called the Ames room, and it was invented by American ophthalmologist Adelbert Ames in 1934. And you can see again, it looks very cool because you can see that when they switch places, these two women actually are the same height. So it was designed to manipulate distance cues to make two same-sized women appear very different in size. It's kind of freaky, isn't it? And so that kind of shows you how it's done. So nature versus nurture in terms of our visual perception. This man became blind between the ages of 3 and 46, and then people who have grown up without vision but then have surgically gained sight in adulthood, as this man has, as a result they could interpret depth, motion, and figure ground distinctions but could not differentiate shapes or even faces. So animals raised at an early age without seeing horizontal lines later seemed unable to learn to perceive such lines. So there's a critical period for the development of our rods and cones to perceive certain stimuli, and so if we miss this critical period like this man did, therefore there's certain images that we cannot see. So because he lost vision at age 3, when he regained it at age 46, he could no longer see distinguish faces. So if humans don't have full visual sensation experience at a critical period of development, we seem to acquire limits to what our brain can interpret from visual stimuli. So there are ways that we can adapt perceptually. So after our sensory information is distorted, such as by a new pair of glasses or by delayed audio in a television, humans may at first be disoriented but can learn to adjust or function. I can tell you that when I grew up, we didn't have cable TV, and back in the day we used to have rabbit ears to watch TV. So many times I would get very kind of staticky channels, but I quickly learned to adapt and view images that were very much distorted, and I would watch TV because I was so desperate to. So this man on the right could eventually learn to fly an airplane wearing these unusual goggles, but here at first he is disoriented by having his word turned upside down, so he can't even, for example, shake this guy's hand. He can't figure out where the hand is, but now but then eventually he was able to adapt. So extrasensory perception, or ESP, can be defined literally as perception without sensation. However, this definition would also include dreams and hallucinations, both which involve perception without sensation. So these are, having thoughts or feelings or visions without actually there being some visual stimuli. People who believe in ESP thinks that it involves getting accurate information directly into the mind, skipping the known senses. Different types of ESP include telepathy, so reading messages from other people's mind; clairvoyance, seeing remote events, so that's when we can see into the future; precognition, also knowing the future. So the evidence right now for ESP is anecdotal and controversial. People seem to notice times when predictions come true and perceptions match reality, but tend to disregard times when they do not. So whenever we have, a premonition and it comes true, then we say, oh, I definitely kind of have this precognition or clairvoyance. Or if you kind of guess what somebody is thinking, then you have telepathy. But if you fail to take into account all the times that you made these guesses and they were inaccurate. So these were kind of just either educated guesses or lucky guesses.